Hi everyone. So in this video, we're going to expand upon our knowledge of the ideal gas law and focus on some of the limitations where it doesn't work the best. So let's go ahead and get started. The first thing I want you to do is to think about it and to go ahead in your notes, draw a picture showing 10 gas particles under the different conditions. So one is high pressure and one is low pressure. So for a hint, think about how volume will affect this. Go ahead, pause the video, make your drawing, and then come back. Okay, so what you hopefully drew is a picture something like this. For high pressure, we have a smaller volume and the particles are closer together. Versus low pressure, we have a much bigger volume or space the particles can occupy, and they're more spread out. So, next thing to think about, what happens to intermolecular forces, so the forces between different molecules, so London dispersion forces, hydrogen bonding, and dipole-dipole interactions, as those particles get closer together. Well, as they get closer together, those forces are going to be stronger because they can feel the attraction of one another. If your particles are spread far apart, they're not going to even know that another particle is around. So as they get closer together, the intermolecular forces get stronger. So now, compare the relationship between IMFs and the average kinetic energy as the particles undergo condensation. So as they go from being a gas to a liquid. Well, as this happens, the average kinetic energy decreases relative to the intermolecular forces. So the intermolecular forces now have a greater role than the average kinetic energy. So this all leads to limitations of the ideal gas law. So the ideal gas law is super important. I guarantee if you go on to college, you will see this in your college chemistry classes. However, it's only accurate about 95% of the time, and it's really, really good for most conditions. So around average temperature and pressure, so room temp and then pressure that we have on a daily basis, about 1 atmosphere. However, as the pressure increases or if the temperature decreases too much, the ideal gas law becomes less accurate. And this is all due to assumptions that we make with the ideal gas law. The first assumption is that the volume of the particle is negligible compared to the overall volume occupied by the gas. Basically meaning that there's a ton of space between the particles, so they take up a lot of space, but the gas particles themselves are not very big. Well, at atmospheric pressure 1 atm, the oxygen molecules will occupy about 0.13% of the volume. So that's a pretty good approximation for standard pressure. But if we increase that pressure much higher to 100 atmospheres, suddenly those oxygen molecules now occupy 17% of the volume. So that is no longer negligible. That's no longer close to zero where we can ignore it. Another assumption of the ideal gas law is that the force of attraction between particles is zero. So if we think about this, when those gas particles are spread far apart, they don't really have a whole lot of IMF attraction. But when we have the particles close to one another, their intermolecular forces are going to be greater. So we know that this is not true because if there was no attraction between particles, then they would never condense to form a liquid. So gas particles do have some amount of attraction, so usually pretty small, but it does get more of a considerable contribution when those particles get closer together. So in order to deal with these assumptions and the limitations they present, we have something called the van der Waals equation, which you see down below. And it is much more complex than ideal gas law, that PV equals nRT. Now we do see portions of it that nRT is still the same on the right-hand side. We kind of see the pressure, but there's a whole lot more going on there. And we kind of see the volume, but again, there's more going on there. So the first part, the P sub real plus A times n squared over the volume of the real particle squared, accounts for the force of attraction between the gas particles. So when you have those gas particles close enough that they have that intermolecular forces that is not negligible, it's actually something measurable, that's where we can account for it. And then the second part of it, the V real minus NB, accounts for the volume of the gas molecule. So again, when we are at that high pressure, the volume of the gas particles no longer is negligible. And in both of these cases, the A and the B are constants, and they are unique to each gas. So oxygen has a different one than nitrogen, from helium, so on and so forth. And you can find them using a table of values that is in your notes. So let's go ahead and compare two different scenarios. So what is the pressure of 1 mole of carbon dioxide at 0 degrees Celsius? And first, we're going to do it at 22.4 liters. So kind of what we would expect under normal conditions. So let's go ahead and plug these values into both the ideal gas law equation and into the van der Waals equation. So when we plug in all of our values for the ideal gas law, we get a pressure of 1.00 atm. Okay, so I'm just plugging in all those values with a volume of 22.4. So when those particles have enough space between them, that their volume pretty much is negligible and there's not a lot of attraction between them. Now, if we go ahead and do the same calculation, same values, but plug those into the van der Waals equation, number one, we see it's much, much more complex. Okay, I will never make you do the van der Waals equation. I just kind of want you to have an idea that it's out there. So if we go ahead and do this calculation, we get a pressure of 0.995 atmospheres, which if you compare 1 and 0.995, they are basically exactly the same. Okay, there's no real difference between those two values. So in this case, it really doesn't make sense to do the van der Waals equation. It is so much more work, and it's really not giving us that much more of an accurate answer. However, if we change our conditions, so if we go from that 22.4 liters and now we squash it down into a teeny tiny 0.2 liters, okay? So now our particles are closer together, their volume will not be negligible, and their attraction will not be negligible. So let's see how that changes things. Okay, so for the ideal gas law, we go ahead, plug in all of our values, and we get a value of 112 atmospheres of pressure. Now, if we go ahead and do the van der Waals equation, which accounts for those differences, we get a pressure of 52.6. Okay, so if we think about that, 112 versus 52.6. In this case, those are very, very different answers. The ideal gas law is not giving us an accurate idea of what's actually happening, so we would want to use the van der Waals equation. But as I said, I'm going to be nice. I will not make you use it in this class. Just know that it's a thing, it's out there, it gives us more accurate calculations, but it's a lot more work. So we're going to mainly keep our problems at around room temperature, at around standard pressure, and with pressure volumes that allow us to still use ideal gas law and get pretty accurate answers. So to take away, at values around 1 mole per 22.4 liters, so about standard density, and at STP, the ideal gas law gives us a very good approximation of how a gas behaves. So it's perfectly okay just to go ahead and use ideal gas law equation. However, if we have very high pressure, very small volumes, or low temperatures, the van der Waals equation will give us a more accurate description of how the gas is actually behaving in that system. But as I said before, for simplicity's sake, we're not going to use the van der Waals equation in this class. We're just going to use the ideal gas law. So if you have any questions on this, please let me know. Otherwise, have a great day, everyone, and I will see you all later. So I hope this helps clarify some of the limitations of the ideal gas law. Bye.